Alright, so we're going to look at projectile motion. Projectile motion is really nothing new in terms of the kinematics involved, but it is involving two-dimensional kinematics. And so let me illustrate that with an example. Imagine you had like a tabletop or a cliff or whatever it happens to be, some sort of height here with an object being launched from it. This object will be launched horizontally. I'm just going to call it Vx. Okay, launched horizontally from here. In doing so here, so Vx, this is going to move at some height. I'm going to make this dy. Okay, here's this height dy. Again, I'm using y and x's because of our coordinate system. I'm going to make that x and that y. So as this thing moves horizontally, it's going to accelerate down and move at a constant velocity to the right. Okay, and so the shape of it will actually look like it will actually be parabolic in shape. As it accelerates down and moves at a constant velocity to the right, it'll land at some distance d away. I'll call this dx. Now, in fact, in this problem here, we're going to assume that we know dy, we know vx. What we're looking for is this, and so this is what that's what we're looking for there, that dx. Okay, so how to solve for that dx? Well, it turns out that we need to look at our variables that we know. And if it's launched horizontally, okay, I'm going to break this up into x and y components. And I do that by putting a little box and saying, okay, we're going to solve for x. In x, what do we know? Well, we know v. I'm just going to call it v instead of vx, but we know v is equal to vx here. We also know here that we're looking for dx. Okay, we don't know what that is. But if I knew what time was, if I knew how long this took to fall, I could get this from an equation. Okay, because it's a constant velocity, there's no acceleration. Very simple equation to solve for that. I need to know time, so I'm going to run over to the y here and see what I know. In the y, I know something. Now this thing launched horizontally, which means there's actually no component of the y velocity at the beginning. Then it starts accelerating and changing velocity. But at the beginning, vi in fact is equal to 0 only in the y. In the x it's definitely moving, but in the y it's 0. I also know it's accelerating, and a is going to be equal to, well, I'm going to make everything down positive, so I'm just going to say a is equal to g. I also know that the distance is equal to dy. So I basically know all these things here. Now, if I can solve for time based on these variables, I know that the time in the y is exactly the same as the time in the x. In fact, if I knew this, I could just plug it into here. So let's see if we can solve it here and what equation we would use. Well, knowing these variables, I would want to use this equation, d equals vit plus a half at squared. Okay, and again, this is 0 because vi is 0. And so that all equals 0. Now if I move this around to solve for time, I'm going to get here time is equal to 2d, because half is the same as 1 over 2, divided by a and square root. So there's time, and I can plug that into here. And in fact, I'm going to use my variables here and say time is equal to 2, instead of d, it's dy, and instead of a, I'm going to write g. And in fact, this ultimately results in that this results in that dx, okay, the distance it moves, will be equal to vx times t. Well, vx we know, time is this new time, so in fact it'll be vx times the square root of 2 dy over g. And there's my final answer. That's how far it moved from the base of the cliff. Looking at this example here, we can think of the graphing that's involved in here, okay, and how to do these graphs. Well, if I separated these things out into x and y, okay, looking at this picture here, in the x, what is happening here? Well, if I was going to look at, let's say, a dx graph versus time, what would it look like? Well, as you can see, it's moving, if I'm going to make it to the right positive, it's moving at a constant velocity to the right. A constant velocity to the right. It's moving away. And so I'm going to represent that. I'm going to start it at 0. And basically it would look just like this. This is what dx and time would look like. What would dy and time look like? Well, for this example here, it's definitely accelerating. And if I make down positive, okay, if I make down positive and this positive, if I make down positive, it's going faster and faster and faster. It's going further away from here. In other words, its speed is increasing as we go down, which means its slope of this graph should increase. And in fact, this graph would look something like this, starting at 0 and then increasing. So you notice the difference between graphs if you look at it, if I'm looking at the y or if I'm looking at the x. It changes. Projectile motion is an interesting thing in that there's often questions where you want to find what's called the range. Okay, to solve the range. If I had a question here, and I'm going to put level ground here, and there's an object that's going to be launched from the ground at some speed v and some angle theta. Okay, some speed v and some angle theta. The range is essentially, if this thing moves and it falls back down, this would be your range. It's your horizontal distance. Okay, I'm going to call that your range. I'm going to get a symbol r. It is dx. You could call it dx as well, but I'm going to call it r for now. This is your horizontal range. In order to solve for this, we can look at what we did before. Okay? The challenge is that this thing's actually launched at an angle and isn't launched horizontally, which means we have to break these up into components. So I'm going to look here and say, well, there's going to be a Vx, there's going to be a Vy. And in fact, relating it to this angle, Vy will be equal to V times the sine of theta. Vx will be equal to V times the cos of theta. And then let's break it up into our known quantities here of x and y. Well, in the x, okay, what do I know? Well, I know here that it's going to be Vx will be equal to V cos of theta. I know that the distance will be equal to the range. That's what I'm looking for. Okay, this is what I want to know. And again, I need to know this guy, time. And so I'm going to save this right now and go to the y and solve for time. In order to solve for time, Vi, well, Vi is not 0 anymore. It's actually equal to V sine theta. So Vi will be equal to V sine theta. I'm going to jump ahead here and say, well, what is the final velocity when it hits? The final velocity in the y will be exactly the same as the initial, because it accelerated just as much up as it did down. And so, in fact, Vf will equal V sine theta, but in the opposite direction. So I'm going to write that as negative V sine theta. And in fact, if I'm writing negative, that means my acceleration also has to be negative the whole time. I'll write negative g. And so then I'm looking for time. I can jump to this equation that says Vf equals Vi plus At and solve for time. And time, I'm going to get Vf minus Vi divided by A. Looking at this, I'm going to get negative V sine theta minus V sine theta all divided by negative g. Well, the negatives are going to cancel each other out, and I'm going to get here time is equal to v squared, or pardon me, 2v sine theta divided by g. So I get that for time, and I can plug that into here. I can actually plug this as 2v sine theta all over g. Well, now solving for the range, I can plug in some numbers here. And the range, okay, will be equal to basically Vx times t. So I can basically solve for Vx times t, in which case that will be V cos theta times, this is Vx, times time, which is 2v sine theta over g. I can simplify this even more. There's two v's here. They're multiplied by each other, in which case I'm going to get here that the range, I'm just going to move it down here, will be equal to v squared, okay, and that takes care of these two guys, times 2 sine theta cos theta all over g. Well, it turns out that this right here, okay, 2 sine theta cos theta, it turns out that's a trigonometric identity. And it actually equals the same thing as saying sine of 2 theta. So I'm just going to simplify this one last time here and just say that the range is equal to v squared sine of 2 theta all over g. And there's my final answer. Okay, there's the range. The initial velocity v sine of 2 theta divided by g. This 2 theta results in something interesting in that it shows that the sine of, let's say, 20 degrees is actually the same as the sine of 70 degrees. So in fact, there actually is two different angles that you can launch something at to get the same range. This will be something you'll see later on, but it has some interesting ramifications in that two angles can actually have the same range.